Hey guys, welcome back to Biomechanics 1 lecture video series looking at part 2 where we're going to be unpacking velocity. So in the previous video we finished off with speed. We defined speed as a change in total distance traveled divided by the total time elapsed. We realized it's a scalar quantity, meaning it only gives us a value without any direction assigned to it, right? So I'm only moving at 5 kilometers per hour, 20 kilometers per hour, without taking account of the direction of motion. That's where something like velocity comes in, because it allows us to account for that direction of motion. So velocity is defined as the speed and direction of motion. Right, it counts for both of those. It has magnitude and direction, and is therefore known as a vector quantity. Right, vector quantities have magnitude and direction, and can be something like velocity, acceleration, force, so on and so forth. Even friction is a vector quantity, right? It takes account for the direction in which something tends to be moving. Okay, really important distinction between the two there. By definition, therefore, when we look at average velocity, same way that we looked at average speed, it's denoted with a V and a little bar on top. Always means average velocity, and is defined as some change in position divided by some change in time. Okay, so we'll just unpack each of those a little bit more just to make total sense of it. So delta x, that's what this little triangle means. This delta means change in, and then the x accounts for the position. Delta x means it's some change from the final position relative to some initial position. Okay, so essentially what does that mean? So let's say, for example, I was standing and I was interested in moving from some position to some other position, right? So if I take my initial position, I just describe a number 0 to it, and I said, okay, I'm interested in moving either left or right at some given speed. I have to account for the direction. So conventionally we always say any movement to the right is given a positive value, and any movement to the left is given a negative value. Okay, it's a really important distinction, because for calculations later on, the value that I ultimately end up with will give me a wealth of information, right? If I have a velocity that I'm trying to calculate and I end up with a positive number, I know that I must have moved to the right. If I end up with a negative number, I know I must have moved to the left. In terms of my second component of my calculation, this delta t here, applies the same convention. It means that there's some final time that I subtract from, or some initial time that I subtract from my final time. Okay, let's just try and put this to some good use. So if I started here at some initial position and I moved to the right, say for example 5 meters, and I did that in 1 second, well, let's make it 10 seconds, right? I moved 5 meters in 10 seconds. This is the position where I ended up, so that's my final position. So if this is my initial position and this is my final position, then this difference in between here is my delta x, right? I can calculate the size of that by just saying it's my final position minus my initial position, the 5 minus 0, which tells me it's 5 meters in total, right? Doesn't seem like rocket science, but this is still keeping things simple. Okay. On the other hand, let's say I moved really far, and not that far. Let's say that I moved 10 meters and it took me 20 seconds to do so, right? This is negative 10 meters because I have to account for the direction in which I'm moving relative to my starting position. I moved to the left of where I started, therefore it's negative 10 meters to the left, right? Again, this would be my new delta x, and that's my final position, which is that over here, minus my initial position, which is equal to negative 10 minus 0 still stays negative, right? So the negative means it didn't get less or smaller or anything like that. It's just telling me the direction in which I move. Negative means to the left. Okay. If I still look at the time values, right? Initially it took me 10 seconds to move to the right, and it took me 20 seconds to move to the left. Gives me some important factors that I need to consider, right? The fact is that delta x can be positive, it can be negative, or it can be 0, right? I move to the right as positive, I move to the left as negative. It's 0 if I stay on the same spot. So if I stay on the same spot for 5 seconds, so even though time's elapsed, I haven't moved, which means that my change in position is 0 because I didn't change position, right? Seems straightforward enough. Delta t, on the other hand, is always some positive number, right? It doesn't matter if I move to the left or right, it's still going to give me a time that it took to cover those distances. If I took 10 seconds to move to the right and I took 20 seconds to move to the left, I don't ascribe a sign to it. It's a scalar quantity. It only gives me magnitude. Okay. So in position 1, if I wanted to calculate just the average velocity of what it took me to move to the right, it's equal to my delta x over my delta t. So again, just making sure I write it all out to not induce any confusion. I plug in the values, which I've essentially already done. So I moved 5 meters to the right. I started at some initial 0 position. It took me 10 seconds. I started the stopwatch from 0 and just timed how long it took me to cover that. So I sit with 5 over 10, which gives me 0.5 meters per second as my average velocity. When I was moving to the left, so my average velocity in situation 2, exact same method of solving, delta x over delta t. That's again my final position minus my initial position divided by my final time minus my initial time. Right, just plug the values in that I had. I moved 10 meters to the left, negative 10 minus 0. That took me 20 seconds to cover that, so I sit with negative 10 over 20. That's negative 0.5 meters per second. Okay, so you'll agree with me that moving to the right, I moved with 0.5 meters per second. Moving to the left, I moved with 0.5 meters per second. Just because it's a negative 0.5 doesn't mean it's smaller, doesn't mean it's decreasing. The sign that is associated with it just gives me the direction in which I tend to move. And it's like we were saying here, or an important factor that comes out of it is the fact that average velocity tends to pick up the sign of the change in position, the delta x. Right. So we said if delta x is positive, negative, or 0, velocity, average velocity will be positive, negative, or 0. Okay. Great stuff. So let's apply that to our second concept test. In this concept test, it's the same as what we did when we looked at average speed. We start in Port Elizabeth, travel 50 kilometers to Uitenhage in 1 hour. We wait in Uitenhage for 1 hour and then race back to PE, those 50 kilometers in half an hour. What in this case is the average velocity of the round trip given the same choices? It's either 0 kilometers per hour, 67 kilometers per hour, 40 kilometers per hour, 75 kilometers per hour, or none of these. I'd encourage you guys to just pause it, try and work it out based on the definitions that we've just covered and see what answer you come up with and compare your reasoning to the ones that are provided in a second. Okay, I'm assuming you guys went through that, so let's just try and make sense of what our answer is. Based on this, your answer should have been 0 meters per second. Remember that the definition for average velocity is the change in position over the change in time. Well, I started in PE and I finish in PE, right? So if this is my 0 mark, this is my 0 mark, and I travel 50 k's that way and I travel 50 k's back, what is my final position? 0. What is my initial position? 0. So if I plug those values in, x of f minus x sub I over whatever time it took me to cover that, I just simply get 0 minus 0 over some change in time, which is going to be 0 meters per second. Drastically different answer to what I got for my average speed, right? So the fact that I'm accounting for changes in position is really, really important here. It might not make so much sense when I look at examples such as this, but it definitely has its place. There's a reason why we distinguish between something such as speed and something such as velocity. They both are critical for certain calculations, and each has its own use in each of those different situations, right? Speed can often be denoted as just the absolute value of v. So if I take you back for a second, I have some velocity here of 0.5 when I moved to the right, and I have some velocity of 0.5 when I moved to the left, but my speed is still 0.5. The sign just tells me which direction. So that's what I was saying when I refer to speed just being the absolute value of v. If I take the absolute value of something, it basically gets rid of any sign that's associated with it, right? So my speed in both instances was 0.5 meters per second. The direction was either left or right. So it's a way of kind of relating speed to velocity. Okay, so you might just see me use that terminology in specific situations going forward. Okay, I'll leave it there for now. And part 3, we'll look at some graphical analysis to show how velocity is related to the change of position, and look at plotting some graphs and making sense of each of those different graphs. Okay, so I'll leave it there for now and see you guys in part 3.